Well, welcome back to our course on system engineering. We're going to be talking about evaluation and selection. And just to give some context, let's go back to our content slide to give some perspective. And so we had our initial introduction. Now we're working our way through the first of three major areas. First, we need to be doing the concept development. Then we get into the engineering development, and then we do the operational and the deployment of the system. And so for this lecture, we're going to be getting the information from the functional analysis and now getting into the evaluation and selection process. So let's go ahead and get started. And so we begin by talking about the evaluation and selecting the system concept. So the physical implementation of the alternative functional approaches involves the examination of different technological approaches, generally offering a more diverse source of alternatives. As in the case of examining alternative functional concepts, the objective of exploring implementation concept is to consider a sufficient variety of approaches to support the definition of a set of system performance requirements that are feasible of realization and practice and do not inadvertently preclude the application of an otherwise undesirable concept. To that end, the exploration of system concepts needs to be broadly based. Evaluating the various system concepts may also require some applied mathematical techniques so as to maximize the performance and minimize the cost for the entire system. By developing a range of performance and cost profiles, the system engineer can provide the decision makers with a variety of choices for the system concept. The system engineer will also rely on the cost analysis to help make sense of cost elements to consider. Well, let's discuss alternative analysis. The full alternative space should be considered when evaluating the design elements. After the functions for the system concept have been defined and validated, the systems engineer should then consider how the design may be developed in order to effectively execute the functions. Considering the full alternative space allows the systems engineer to identify the constraint space, such as what needs to be addressed and considered. Perhaps this accounts for the operational environment constraints for the system to work in and or other organizational constraints that the system must operate in and account for other organizations. Some of the constraints may include performance, cost, or schedule. Performance constraints may include interoperability, timing, formatting, or language, to name a few. Cost constraints may limit the system engineer to selecting portions of the design that would fit under the budget caps and may potentially reduce the overall effectiveness while remaining under the physical constraints. Schedule constraints may also limit the systems engineer to select portions of the design that will be compatible with the desired overall system schedule, even if this may be a suboptimal system in totality. One approach is to identify all the possible combinations of system designs, regardless of the constraints. This may allow the system engineer to then work through each part of the system in order to satisfy all the constraints levied upon the system concept. This may originate with identifying which of these three constraints, that is performance, cost, and schedule, has the most limiting factors, and then work through each of the different constraints until a satisfactory system design arises. Okay, in terms of the alternative implementation concepts, the predecessor system where one exists forms one of the spectrum to be explored. Given the operational deficiency of the predecessor system to meet projected needs, modifications to the current system concept should first be explored with a view to eliminate those deficiencies. Such concepts have the advantage of being relatively easy to assess from the standpoint of performance, development risk, and costs than are radically different approaches. There can also generally be implemented faster, more cheaply, and with less risks than innovative concepts. On the other hand, they are likely to have severely limited growth potential. The other end of the spectrum is representing by innovative techniques, approaches featuring advanced technology. For example, the application of powerful modern microprocessors might permit extensive automation of presently employed manual operations. These concepts are generally riskier and more expensive to implement, but offer large incremental improvements or cost reduction and greater growth potential. In between are intermediate or hybrid concepts, including those defined in the needs analysis phase for demonstrating the feasibility of meeting the proposed system needs. Many techniques exist for developing new or innovative concepts. Perhaps the oldest is brainstorming, individually and with a group. Within the concept of brainstorming, several modern methods of variations to the old-fashioned, largely unstructured brainstorming process have arisen. The natural temptation to focus quickly on a single concept or point design approach can easily preclude the identification of other potentially advantageous approaches based on fundamentally different concepts. Accordingly, several concepts spanning a range of possible design approaches should be defined and investigated. At this stage, it is important to encourage creative thinking. It is permissible, even sometimes desirable, to include some concepts that do not meet all of the requirements. Otherwise, a superior alternative may be passed by because it fails to meet what may turn out to be a relatively arbitrary requirement, such as the needs analysis phase. Negotiations with the customer regarding which requirements are really necessary and which are not can often make a significant difference in cost and risk factors while having minimal impact on performance. Well, let's consider an example. Let's consider the concept exploration for a new aircraft. Two principal functional operations to be explored are a propeller-driven and a jet-driven aircraft. It remains to explore alternative physical implementations of each of these options. As is usually the case, these are more numerous than the basic functional alternatives. A host of technological advances continue to be developed. For example, automation has become more widespread, especially in autopilots and navigation systems. Autonomous planes can be in the future. Changes in safety requirements, such as de-icing provisions, may also be examined to identify those performance characteristics that should be called out. In exploring alternative implementations, the main features of each candidate system must first be analyzed to see if they are conceptually achievable. At this stage of development, a detailed design analysis is usually not possible because the concept is not yet sufficiently formulated. However, based on previous experience and engineering judgment, someone, usually the system engineer, must decide whether or not the concept as proposed is likely to be achieved within the given bounds of time, cost, and risk. There are numerous other options and variations that have pros and cons, which typically leave the customer with no obvious choice. Note also that the option to use jet aircraft may partially violate the operational requirement that short route capability be maintained. However, as noted earlier, it is not at all unusual at this stage to consider options that do not meet all of the initial requirements to ensure that no desirable option is overlooked. The airline may decide that the loss of some routes is more than compensated by the advantages to the overall system of using jet aircraft. It is also important to note that the entire system life cycle must be considered in exploring alternatives. For example, when the jet option offers a number of performance advantages, it will require a substantial investment in training and logistic support facilities. Thus, assessment of these supporting functions must be included in formulating system requirements. In order to be a quote smart buyer, the airline needs to have a staff well versed in aircraft characteristics, as well as the business of running an airline, and access to consultants or engineering services organizations capable of carrying out the analysis involved in developing the requisite set of performance requirements. Well, let's think about preferred systems. Although in most cases it is best to refrain from picking a superior system concept prematurely, there are instances where it is permissible for the requirement definition effort to identify a so-called preferred system, in addition to considering a number of other viable system alternatives. Preference for a system or subsystem may be set forth when significant advanced development work has taken place and produced very promising results in anticipation of future upgrades to the current system. Such work is often conducted or sponsored by the customer. Another justifying factor may be when there has been a recent major technological breakthrough which promises high gains in performance at an acceptable risk. The idea of a preferred system approach is that subsystem analysis can start building on the concept, thereby saving time and cost. Of course, further analysis may show the favored approach not to be as desirable as predicted. Well, let's also consider the technological development, whether the origin of a new system is needs-driven or technology-driven. The majority of new systems have been brought into being directly or indirectly as a result of technological growth. In the process of exploring potential concepts for the satisfaction of a newly established need, a primary input is derived from what is called the technology base, which means the sum total of the then existing technology. It is therefore important for systems engineers to understand the nature and source of technological advances that may be pertinent to the proposed system development. System-oriented exploratory research and development, research R&D, can be distinguished according to whether it relates to new needs-driven or technology-driven systems. The former is mainly directed to gain a firm understanding of the operational environment and the factors underlying the increased need for the new system. The latter is usually focused on extending and quantifying the knowledge base for the new technology and its application to the new system objectives. In both instances, the objective is to generate a firm technical base for the projected system development, thus clarifying the criteria for selecting specific implementation concepts and transforming unknown characteristics and relationships into knowns. Both industry and government support numerous programs of R&D on components, devices, materials, and fabrication techniques which offer significant gains in performance or cost. In recent years, the greatest amount of technology growth has been in the electronic industry, especially computers and communication equipment, which in turn has driven the explosive growth of information systems and automation. In government-sponsored research and development, there is also a continuing large-scale effort, mainly among government contractors, laboratories, and universities, directed towards the development of technologies of direct interest to the government. As has been noted previously, defense contractors are permitted to charge a percentage of their revenues from government contracts to independent research and development, IRAD, as allowable overhead. A large fraction of such funds is devoted to activities that relate to the potential new system development. Well, we also have performance characteristics to consider. The derivation of performance characteristics through the exploration of implementation concepts can be thought of as consisting of a combination of two analytical approaches. Performance analysis and effectiveness analysis. Performance analysis derives a set of performance parameters that characterize each candidate concept. Effectiveness analysis determines whether or not a candidate concept meets the operational requirements, and if not, how the concept needs to be changed to do so. It employs an effectiveness model that is used to evaluate the performance of a concept system design in terms of a selected set of criteria or measures of effectiveness. This is a similar model to that used in the previous phase and to the one employed in the next step, the validation of performance requirements. The main difference is the use in the level of detail and rigor. In terms of performance analysis, the performance analysis part of a process is used to derive a set of relevant performance characteristics for each candidate system concept that has been found to satisfy the effectiveness criteria. The use of relevancy arises because a full description of any complex system will involve many parameters, some of which may not be directly relevant to its primary mission. For example, some features, such as the ability of an aircraft search radar device to track some particular coded beacon transponder, might be included only to facilitate system test or calibration. Therefore, the performance analysis process must extract from the identified system characteristics only those that directly affect the system's operational effectiveness. At the same time, care must be taken to include all characteristics that can impact effectiveness under one or another particular operating condition. The problem of irrelevant characteristics is especially likely to occur when the concept for a particular subsystem has been derived from the design of an existing subsystem employed in a different application. For example, a relatively high value of the maximum rate of elevation for a radar antenna assembly might not be relevant to the application now being examined. Thus, the derived model should not reflect the requirements unless it is determining factor in the overall subsystem design concept. In short, as stated previously, the defined set of characteristics must both necessary and sufficient to facilitate a valid determination of the effectiveness for each candidate system concept. And in terms of constraints, at this phase of the project, the emphasis will naturally be focused on active system performance characteristics and functions to achieve them. However, it is essential that other relevant performance characteristics not be overlooked, especially the interfaces and interconnections with other systems or parts of systems, which will invariably place constraints on a new system. These constraints may affect physical form and fit, weight and power, schedule, for example, a launch date, mandated software tools, operating frequencies, operator training, and so on. While constraints of this type will be dealt with in greater detail later in the development process, it is not too soon to recognize their impact during the process of requirement definition. The immediate benefit of early attention to such problems is that conflicting concepts can be filtered out, leaving more time for analysis of the more promising approaches. Well, next, we'll be discussing operations research techniques, and so we'll give some overview. We'll also show some examples and give enough details about each one of those so that you can get a good idea of what's going on. So a brief introduction to different operational research techniques is provided for the system engineer to consider and apply while developing the system concepts and considering the alternative space for the design. Each of these techniques may allow calculation of different aspects of the system and should be used to converse with the stakeholders on what is most important about the system. Well, let's consider optimization techniques, and we'll look at the assignment problem to minimize machines. That's what we're going to be showing here in the figure. And so optimization seeks to minimize or maximize a selected attribute of the system. Some classic optimization examples are how to maximize profit by identifying how many different products should be developed and sold for, thus minimizing the limited resources to develop a product and maximize the expected profit. Linear programming, or LP, is a technique that may be used to find a maximum or minimum value to achieve the best outcome. Examples may be to maximize profit or minimize costs. This technique can also be applied to identifying exactly how many transportation platforms are needed to address the product demand, such as cities giving a finite number of resources, such as warehouses, and the distance from source to destination in order to minimize transportation costs while satisfying all market demands. LP assumes that the change in the variable will correspond linearly to the outcome. A subset of LP is called integer programming, where all of the decision variables are in integers. This can be useful when solving for whole numbers of units, such as vehicle allocation, X-ray machines, or computers. An example of LP is shown in this figure. And so this is a problem that seeks to minimize the total number of systems to be used to satisfy all functions. Another objective is to minimize the total cost, as each machine can perform multiple functions. This example identifies 6 systems labeled A through F and 10 functions. The 1 indicates the system can perform the function. And we were highlighting those and have colorized them. The LP example is set up to select whether or not the system is used. 1 is yes, 0 is no, and totals the cost as well as accounts for each of the functions satisfied. The coverage row should equal the desired coverage. Additional constraints can be added if there is a threshold for duplicative functions being performed, so as to minimize the amount of duplication in the answer. The final result is shown with systems B, C, E, and F required for use to satisfy all functions with the minimal cost. The system engineer can use tools such as this to perform the what-if analysis at an early phase of the system engineering lifecycle in order to explore how the total system concept may look like. Well, let's talk about decision making, and we'll also walk through a decision tree example in this process. Decision making is a quantitative technique to identify the decision space, for example, all the possible decisions and the possible outcomes and likelihood of the decision path to occur. Using a graphical depiction of the decision tree may provide stakeholders with insight into what may be evaluated and considered. In order to see the full scope of decisions and which stakeholders may be affected, the decisions are developed to assist decision makers in identifying alternative decision paths and evaluating and comparing different courses of action. The concept utilizes probability theory to determine the value or utility of alternative decision paths. As the name suggests, a tree is used to formulate the decision space. Typically, 2 symbols are used, one for decisions and one for events that could occur and are out of the decision maker's control. So in this figure, it depicts a simple decision tree in which 2 decisions and 2 events are included. The decisions are depicted by the rectangles and are lettered A and B. The events are depicted by the circles and are designated E1 and E2. In this example, each decision has 2 possible choices. Events have more than one outcome, with probabilities associated with each. Finally, the value of each decision path is shown to the right. A value can be anything that represents the quantitative outcome of a decision path. This includes money, production, sales, profit, etc. So moving on, in this example, an engineer is faced with an initial decision. Are the two choices A1 and A2. If one chooses A2, then an event will occur and provide a value of either 100 or 30, with probability of 0.1 or 0.9 respectively. If one chooses A2, you're immediately faced with a second decision, B, which also has two choices, B1 and B2. Choosing B2 will result in the value of 40. Choosing B1 will result in an event E2 with two possible outcomes. These outcomes result in values of 70 and 30 with probabilities of 0.3 and 0.7 respectively. Which decision path is best? The answer to the last question is dependent on the objectives of the trade-off study. If the study objective is to maximize the expected value of the decision path, then we can solve the tree using a defined method, which we would not go through in detail here. Basically, an analyst or engineer would start at the values to the right and work left. First, calculate the expected value for each event. Then at each decision point, choose the greatest expected value. The expected value is the weighted sum of the legs of the diagram, and select the winner and write the value in the circle or square. In our example, calculating the events yield an expected value of 100 times 0.1 plus 90 times 30, which is equal to 37 for E1. And then for E2, it's 70 times 0.3 plus 30 times 0.7, which is 42 for E2. Thus, decision B is between choosing B1 and gaining a value of 42 over B2, which with a value of 40. Decision A is now between the two expected values. A1 yields a value of 37, while A2 yields an expected value of 42. Thus, choosing A2 yields the greatest expected value. So we're showing that in this next phase of exploring this figure. So finishing up on this figure, of course, the objective may not be to maximize expected value. It may be to minimize expected loss or minimize the maximum loss or even maximize value. If the objective was the last of these three, maximize value, then choosing A1 would be preferred since only A1 yields a possibility of achieving a value of 100. So we can see that choosing A2 yields a maximum possible value of only 70. Thus, the objective of the trade-off study determines how to solve these trees. An alternative method of using decisions tree is to add a utility assessment. Based instead of using values, we use utility. The reason we may want to substitute utility for actual values is to incorporate risk into the equation. Suppose, for example, that we have the decision tree that we're listing here already solved to maximize expected values. However, the customer is extremely risk adverse. In other words, the customer would forego larger profits than lose large amounts of value. In this case, the value could be profits. It should be noted that numerous automation tools are available to facilitate these explorations, whether through multiple attribute decision-making or set-based decisions. There is a large body of published works devoted to these topics, and the textbook refers us to trade-off analytics, creating and exploring the system trade space by Parnell. And so it's a book that discusses these topics at an depth suitable for practicing systems engineers. Next, we'll discuss economics and affordability, and we'll walk through a handful of examples of how this could actually be done. The system engineer could be cognizant of affordability assessments that may help decision makers identify the optimum system concept, understand the resource allocation process, help to quantify stakeholders' expectations, and help to deliver portfolio outcomes that stay within budget estimates. Three main segments of affordability are discussed: cost estimating and analysis, investment decision analysis, and resource efficiencies. So first of all, for cost estimating and analysis, often some initial questions can be asked on how to quantify life cycle costs. The most popular cost estimate is the life cycle cost estimate, LCCE, which provides a cradle to grave estimate. This includes the initial research and development, production, operation / support, and disposal costs. The R&D costs include all program R&D equipment, personnel, facilities, and testing. The production costs include procurement of the initial materials to produce a system, the manufacturing facility, the labor force and training, spares, and any pre-planned product improvements. The operations / support costs includes operating and supporting the system during employment, to include personnel, maintenance, and sustaining investments. Generally, this is the largest portion of the cost of the LCCE. Finally, the disposal costs include demilitarization, detoxification, long-term waste storage, and any environmental restoration efforts that are required. Next, we'll consider investment decision analysis, and we'll get to this figure here as one example when we consider non-monetary benefits. The system engineer should also be cognizant of how much decisions cost, as well as what is the value of the investment and is it affordable. Typically, a cost-benefit analysis would help the decision makers understand the implications of comparing different alternative performance and cost to help down selections or final selection decisions. Elements of a cost-benefit analysis can include define the objectives. It should be clear on what the desired outcome of the study should achieve. Understand the problem. This should bind the problem with both the performance as well as the cost boundaries in order to develop a clear, affordable, and measurable goal. Formulate assumptions and ground rules. Similar to technical performance assumptions, there should also be economic assumptions that will help bound the problem, data collection, and analysis of the data. Identify and examine alternatives. Ideally, here, there should be a minimum of 2 alternatives: the existing, quote, as is system that provides a baseline of understanding and point of reference, in the future, quote, to be alternative that is proposed. There could be several alternatives that are under considerations beyond that. Develop cost and benefit estimates. There could be organized into monetary and non-monetary benefits. Monetary benefits can be categorized into 3 areas. The first is cost savings, where selecting the alternative may generate a reduced budget requirement in the future. The second is cost avoidance, where the alternative provides a future cost savings or causes a reduction in future resource requirements. The third is to improve productivity, where the alternative affects an improvement in ability, efficiency, and/or quality of getting work done. Non-monetary benefits can evaluate the system objectives, the criteria on how the objective is satisfied, and the measures by which to evaluate the performance of the alternatives. This may be more oriented towards the performance rather than the monetary aspects, and the system engineer should ensure that these performance and cost elements are evaluated separately. So we're showing here as an example of a lawn mower and the evaluating the performance. And so this is laid out here in the figure. So we'll move on here, and we'll also discuss the scatter plot of cost and performance that we're showing. All alternatives can be compared and ranked relative to each other to show the relative benefit to satisfy the objective. A scatter plot may be used to graphically display the performance and costs. Other means of comparing the alternatives may be using multiple criteria decision analysis techniques in order to evaluate the weighting / importance of the evaluation criteria and to assist the decision makers on how the alternatives satisfy the most important criteria. So this figure provides an example of a scatter plot of cost savings versus performance. The error bars in each axis can indicate the uncertainty in the calculations or show the range of performance and cost to the decision makers. Baseline systems should also be included in the chart in order to provide a comparison of how well the alternatives perform and cost to the existing system. In this case, the alternative with the highest cost savings and highest performance, the top right quadrant of the chart, would be the preferred alternative. We can also consider cost context, and so we're showing a diagram for that. So continuing on with our discussion, similar to performance evaluations where sensitivity analysis is conducted on selected criteria, cost criteria may also be modified to determine the impact to the overall selection. Finally, a final recommendation must be made as well as providing justification to these selected criteria. Well, what about resource efficiencies? Questions that can be asked include, how do we make an efficient use of the resources, or what are the best courses of action to follow given a resource constrained environment? Again, a comparison from the baseline or current system is needed to help compare the relative benefits of the alternatives. Identification of the most important performance / monetary criteria is also key to determine which alternative should be pursued. Defining the workflow of the system activities and usage of the resources may also be needed in order to calculate how well different alternatives can provide comparative advantages over the baseline system. Sometimes a context diagram can assist the systems engineer to identify the different cost elements of a system and then to calculate the most critical cost components in order to perform the analysis. So in this figure, we're showing an example of a context diagram to discuss various healthcare costs. The inner circle represents the broad categories, and the outer circle represents different contributions. The system engineer can then use this diagram to dialogue with system decision makers to help identify which of the most important factors to examine for improvements of efficiency. Well, next, let's discuss events and decisions for considerations. The typical decisions made during the system engineering lifecycle. Some of the decisions that are made throughout the system engineering lifecycle will affect how the system will maintain its schedule for development and operations in the intended environment. System engineers should understand the decisions that are made during their system development and will affect the remainder of the project. So here we're seeing a table exploring systems decisions questions, and we'll mention that in a minute. So decisions can range widely concerning the project. We've referred to several system acquisitions references to identify the decision points on whether a system should proceed to the next step of development or to cease operation. So as this lecture and the corresponding chapter relates to evaluating and selecting, we would focus the decision makers on how well the candidate system concepts performed. We consider the system context diagram and ask several questions regarding the performance, cost, and utility in order to evaluate selected decisions which are found in this table. And so we're showing these kind of questions we want to consider. Other organizations may be concerned with different decisions based on the industry, stakeholder responsibilities, public safety, or other factors. The Department of Defense uses a series of acquisition milestones, MS, to evaluate system development progress, which are summarized briefly. Milestone A decision decides whether or not to invest in the technology maturation and preliminary design of a system concept. The milestone B decides whether to invest in product development, integration, and manufacturing. Milestone C decides to produce production representative units for operational testing. So you can refer to the DoD's Defense Acquisition Guide chapters on system engineering, from the Defense Acquisition University for additional information. In contrast, NASA uses key decision points, KDP, to determine whether or not the project/program is allowed to enter the next life cycle phase. Broad phases include expected maturity to address the need, expected state to determine if mission/system architecture is credible, expected maturity of the project's technical/cost/schedule, expected maturity with regard to the project remaining on plan, expected state ready for launch, expected state to conduct mission operations and activities, and expected state for project decommissioning and disposal. So you can refer to the NASA's space flight program and project management requirements for further description of the KDPs. The Department of Homeland Security, DHS, uses an acquisition decision event, ADE, to progress through the system development process. These closely follow the DoD process. The four main phases are justify the need, analyze/select alternatives, obtain the alternatives, and either produce, deploy, and support the capabilities until it is retired. So you can refer to the DHS's Acquisition Management Directive and DHS Instruction Manual for more details. Commercial developers may also evaluate the system development process with other decisions such as market performance, previous customer experience, competitors' focus, the overall economy, the cost to produce, the manufacturing process, to name a few. Based on the results of this exploration, companies may decide to produce or halt the development of the system concept. In COSI, the System Engineering Society has a series of life cycle stages and decision gates on whether to progress to the next phase or not. The life cycle stages start with exploratory, that is investigating new opportunities, concept, which is the evaluating concepts and stakeholder needs, development, which is planning and risk management, production, which is producing and testing, utilization and support, which is operating and providing a sustainable capability, and retirement, which is storage or disposal. You can refer to the INCOSI System Engineering Handbook for more details on that. So in terms of types of resources affected during decision milestones, resources can come in different formats during the system development. Some include people, organizations, technology, security, budgetary, development, say hardware and software, integration, or testing. Resources are often linked to decisions made in the previous phases. The common example is the requirement development in early phases set the resourcing for design and testing in the future phases. If the requirements are found to be developed incorrectly, that would cause an adverse impact to the future resource planning and may cause project delays while revising the requirements. It is imperative that the resources types are planned and accounted for prior to the development phase or key decision points. Some of these resources, such as manufacturing, material, or test ranges, require long lead time to coordinate. Plan for contingency actions if there are unforeseen delays in the project development, and to have some utilization of the resources, such as people shifting to different projects or non-dependent tasks within the project while the project undergoes a delay. The system engineer and decision makers can gain insight into the level of resources needed for these decisions through risk reduction events to examine the utility and assessment of the technology in the envisioned operational environment. This can help develop new concepts and develop requirements for new programs. Other prototyping efforts can evaluate the technical feasibility of a capability. Next, we'll talk about alternative concept development and concept selection, and we'll also have some discussion on formulation of alternative concepts and modeling of alternatives. The decisions in the process of concept definitions center on the selection of a particular system configuration or concept in order to satisfy the function it is to perform. These decisions do more to determine the ultimate performance, cost, and utility of the new system than those in any subsequent phase of the development. Further, in a competitive acquisition process, selection of who will develop the system is largely based on the evaluation of the proposed concept and the supporting documentation. For those reasons, developing the alternatives is a crucial importance to provide the decision makers with a feasible set of concepts to proceed with development. The system engineering method calls for such decisions to be made by a structured process that considers the relative merit of a number of alternatives before any one is selected. The process is called trade-off studies or trade-off analysis and is used in decision-making processes throughout system engineering. Trade-off analysis is most conspicuously employed during the concept development phase, largely in the selection of the physical implementation of system components. Well, let's talk about the formulation of alternative concepts. In the early development phases, the alternative system concept construction begins by allocating the functions identified by physical components of the system. In other words, we must determine how we will implement the functions. Of course, this might entail decomposing the top-level functions in a functional block diagram or other functional representation into lower-level functions. Many times, this activity provides insight into alternative methods of implementing each function. As we identify system components, beginning with subsystems, we are constantly faced with the question of whether multiple functions can and should be implemented in a single physical component. The converse is also an issue. Should a single function be implemented by multiple subsystems? Ideally, a one-to-one mapping is our goal. However, other factors may lead one to map multiple functions to a single component or vice versa. A specific allocation of function to physical components and the functional and physical interfaces that result from the allocations are considered a single alternative. Other allocation schemes will result in different alternatives. The trade-offs mentioned above can occur at multiple levels, from the entire system to individual components. Many times these trade-offs are part of the functional allocation process. An important objective is to ensure that no potential valuable opportunities are omitted. So what we'll discuss next is we'll explore the issues with developing alternatives. First of all, the predecessor system as a baseline. We've thought about this before, but now thinking about in this concept. And so This is the most system developments are aimed at extending the capabilities or increasing the efficiency of some function that is presently being inadequately performed by an existing systems. In cases where the function of the current system are the same or similar to those of the new system, the current system provides a natural point of departure for system concept definition. When the main driving force comes from serious deficiencies or limited portions of the current system, an obvious or maybe a partial set of alternative approaches would begin with a minimum modification of the system restricted to those subsystems or major components that are clearly deficient. Other alternatives would progressively modify or replace other subsystems that may be made obsolete by modern technology. The general configuration of the system would be retained. In cases where there are new and improved technological advances at the component level, or where there are standard commercial off-the-shelf components that could be applied to the new system, the impetus for change to a new system would be technology driven. In this case, a common used approach is to introduce improvement sequentially over time as modifications to the current system configuration. Even when there are reasons against retaining any part of the current system, as for example, when moving from a conventional manually controlled process to an automated and higher speed operation, the current system's general function, configuration, component selection, construction materials, special features, and other characteristics usually provide a useful point of departure for alternative concepts. In terms of technological advances, some new system developments are driven more by advances in technology than by operational deficiencies in the previous systems. These advances may arise either in exploratory research and development programs aimed at particular application areas, such as development of advanced jet engines, or may come from broadly applicable technologies such as high-speed computing and communication devices. Such advances are often incorporated into an existing system to achieve specific performance improvements. However, if their impact is major, the possibility of a radical departure from the previous configuration should be included among the alternatives. Beyond a certain point, the existing framework may overly constrain the achievable benefit and should therefore be abandoned. Thus, when advanced technology is involved, a wide range of choices for change should be examined. For the original new concepts, in relatively rare instances, a really different concept is advanced to meet an operational need, especially when the need has not been previously met. In such instances, there is not likely to be a previous system to use for comparison, so that the different type of alternatives would need to be examined. Often various versions of the new concept can be considered, differing in the degree of reliance on new and unproven technology in exchange for projected performance and costs. In terms of modeling of alternatives, for comparing alternative concepts, each must be represented by a model that possesses the key attributes on which the relative value of the alternatives will be judged. As a minimum, a functional flow block diagram of each should be constructed and pictorial or other physical description produced for providing a more realistic view of the system candidate. Then we get into the concept selection. The object of trade-off studies in the concept definition phase is to achieve the relative, quote, goodness of alternative systems concepts with respect to operational performance and compatibility, program costs, program schedule, risk in achieving each of the above. The results are judged not only by the degree to which each characteristic is expected to be achieved but also by the balance among them. Such a judgment is of necessity highly program dependent because of the differing priorities that may be placed on the above characteristics. terms of design margins, a competitive program, there is always a tendency to maximize system performance so as to gain an edge over competing system proposals. This often results in pushing the system design to a point where various design margins are reduced to a bare minimum. The term design margin refers to the amount that a given system parameter can deviate from its normal value without producing unacceptable behavior of the system as a whole. A reduction in design margin is inevitably reflected in tighter restrictions on the environmentally induced changes in component characteristics during system operation and/or on the fabrication tolerances imposed in the production process. Either can lead to higher program risk, cost, or both. Accordingly, the issue of design margin should be explicitly addressed as an important criteria when selecting a preferred system concept. And then in terms of system performance, cost, and schedule, to the extent that stated performance requirements are quantified, are found to be an accurate expression of operational needs and are within current system capabilities, they may be considered a minimum baseline for the system. However, where they are found to stress the state of the art or to be desirable rather than truly essential, they need to be considered elastic and capable of being traded off against cost, schedule, risk, or other factors. Unstated requirements found to be significant should always be included among the variables. Program cost must be derived from the system lifecycle cost, which in turn must be derived from a model of the complete system lifecycle. The appropriate relative weighting of the near-term versus long-term cost depends on the financial constraints of the acquisition strategy. Specific cost drivers should be identified wherever possible. The appropriate weighting of schedule requirements is program dependent and may be difficult to establish. There is an inherent tendency, especially in programs where competition among contractors is especially strong, to estimate both cost and schedule of a new acquisition on the optimistic side, making no provision for the unforeseen delays that always occur in new system developments and are often called unknown unknowns. The optimism factor also applies to the performance of system performance. Sorry, the optimization factor also applies to the estimation of system performance and technical risk. Overall, it tends to slant the trade-off process towards a selection of advanced concepts and optimistic schedules over more conservative ones. So finishing up on alternative concept development and concept selection, we'll address two concepts here, program risk and also selection strategy. So in terms of program risk, the assessment of risk is another primary system engineering task and involves estimating the probability that a given technical approach will not succeed in achieving the intended objective as an affordable cost. Such risk is present in every previously untried approach. In development of a new complex system, there are many areas in which risk of failure must be explicitly considered and measures taken to avoid such risk to reduce their potential impacts to manageable levels. So we'll see it in another chapter and another lecture. It's devoted to the subject of risk management, and it shows a program risk can be considered to consist of two factors. One, probability of failure, the probability that the system will fail to achieve an essential program objective, and two, criticality of failure, the impact of the failure on the success of the program. Thus, the seriousness of each risk can be qualitatively considered as a combination of the probability of the failure weight by its criticality of the system. For the purposes of what we're going to talk about in this lecture and the related chapter, The following are examples of conditions that may result in a significant probability of program failure. A leading edge unproven technology is to be applied. A major increase in performance is required. A major decrease in cost is required for the same performance. A significantly more severe operating environment is postulated, and an unduly short development schedule is proposed. In terms of the selection strategy, the preceding discussion shows that the principal criteria involved in selecting your preferred system concepts are complex, semi-quantitative at best, and involve comparisons of incommensurables. This means that the evaluation of the relative merits of alternatives must be such as to expose and illuminate the most critical characteristics and allow the maximum exercise of judgment throughout the evaluation process. Two additional guidelines for conducting complex trade-off analysis may be useful. One, to conserve analytical effort, use a staged approach in the selection process in which only the most likely winners are subject to the full set of system evaluation, and two, retain the visibility of the complete evaluation profile of each concept against each critical measure of effectiveness until the final selection, rather than combining the components into a single figure of merit, a practice that is often employed but that tends to submerge significant differences. In pursuing a staged approach, the following suggestions can serve as a checklist to be applied where appropriate. One, for the first stage of evaluation, make sure that a sufficient number of alternative approaches are considered to address all needs and to explore all relevant technical opportunities. Two, if the number of alternatives is larger than can be individually evaluated in detail, perform a preliminary comparison to winnow out the outliers. This is equivalent to qualifying the candidates, but be careful not to discard prematurely any candidate that presents a new and unique technological opportunity unless they are inherently incapable of qualifying. Three, for the next stage of evaluation, examine the list of performance and compatibility requirements and select a subsystem of the most critical ones that are also the most likely to reject unsuitable system concepts. Include consideration of growth capability and design margin as appropriate. Four, for each candidate concept, evaluate its expected compliance with each selection criteria. In the case of partial non-compliance, attempt to adjust the concept where possible to satisfy the criteria. Estimate the resultant performance, cost, risk, and schedule. In the event of conspicuous imbalance in the above, attempt to modify further the concept to achieve an acceptable balance for all requirements. Five, assign weight factors or priorities to the risk evaluation criteria, including cost, risk, and schedule, and apply to the ranking of each concept. Avoid concepts that do not have a sound balance of the above factors. Six, for each evaluation criteria, rank order the several candidate concepts. Seven, look for and eliminate clear losers. Eight, unless there is a single clear winner, perform a significantly more detailed comparison among the two or three potential winners. To this end, develop a life cycle model for each concept, along with a work breakdown structure and a risk abatement plan. In making the final system concept selection, review the evaluation profile, the merit of each candidate concept against each critical measure of effectiveness to ensure that the choice has no major weaknesses. Check for sensitivity of the result to reasonable variation of the weighting of individual criteria. Next, we'll discuss concept validation. The task of designing a model of the system environment to serve as a basis for concept validation builds on the set of parameters initially established for use in the trade-off studies of the selection process. terms of the modeling the system and its environment, since the degree of system definition at this stage is largely functional, its validation must rely primarily on analysis rather than testing. The rapid growth of computer modeling and simulation in recent years is providing powerful tools for the validation of complex system concepts. Concerning the system effectiveness models in complex operational systems, system effectiveness models are developed in the needs analysis and concept exploration phases to provide a further understanding of the effectiveness of existing systems in performing their mission and identifying deficiencies that need to be remediated. These are most often computer simulations that include provisions for varying key parameters to establish the sensitivity of overall performance to environmental and system parameter variations, and to determine the nature and extent of system changes needed to offset any identified deficiencies. In the concept definition phase, the construction of system effectiveness models by the system developer depends on whether or not the model used in the previous phases are available, as in the case where the developer is also the customer. In that case, the models can be readily extended to conform to the selected system concept for the validation process. If not, the construction of the model becomes part of the concept definition task. For this and other reasons, the preparation for the competitive effort often begins months and sometimes years before the start of the formal competition. Computer models are also capable of validating a host of subsystems or component level technical design features. Areas such as aerodynamics design, microwave antennae, hydrodynamics, heat transfer, and many others can be modeled for analysis through the use of special computer codes. Advances in computer capabilities have made such models more and more accurate in predicting system behavior for purposes of design and evaluation. For critical experiments, when a proposed system concept relies on technical approaches that have not been previously proven in similar application, their feasibility must be demonstrated. Often this cannot be done credibly through analysis alone and must be subjected to experimental verification. This is difficult to accommodate in the limited time and constraint resources of a competitive acquisition, but must nevertheless be undertaken to support the proposed system concept. The term, quote, critical experiment is appropriate in such instances because it is related to the specific purpose of substantiating a critical feature of the design. It purposely stresses the proposed design features to the extreme limit to ensure that it is not marginally satisfactory. The term experiment rather than test is appropriate because it is performed for the purpose of obtaining sufficient data to understand thoroughly the behavior of the system element rather than merely to measure whether or not the element operates within certain limits. By the same token, extensive data analysis are also performed to illuminate the system behavior. In terms of the analysis of validation results, the analysis of the results of system validation simulations can produce three different types of unsatisfactory findings that require remedial action. One, deficiency in the assumed characteristics of the system being modeled. Two, deficiency in the test model. Or three, excessively stringent system requirements. It is a purpose of the analysis process to attribute the results of the simulation to one or more of the above causes. Beyond these findings, the analysis should also indicate what kind and degree of changes would eliminate the discrepancy. This latter finding usually requires a series of simulation or analysis that tests the effects of alternative remedial actions. The feedback results from the validation analysis results in an iterative process in which the system model design and environmental models are refined as necessary to bring the system model in compliance with the requirements. In terms of the iteration of system concept and requirements, the above description of the validation process implies that only one concept was found to be superior in the concept trade-off analysis, and that the concept was then validated against the full system requirements. Not infrequently, two or sometimes more concepts turn out to be nearly equal in preliminary ranking. In that case, each should be evaluated against the full requirements to see if the more rigorous comparison produces a clear discriminant for the selecting the preferred concept. The system requirement should always be regarded as a flexible up to a point. If the validation or trade-off results show that one or more stated requirements appear to be responsible for unduly driving up system complexity, costs, or risks, they should be subjected to critical analysis and, if appropriate, highlighted for discussion with the customer by program management. As a final topic, we can consider the traditional versus agile system engineering approach to concept evaluation. So from a concept evaluation and selection perspective, traditional system engineering would proceed in the methodical approach to collect the system objective, requirements, and function, as well as the candidate alternative system concepts. By performing analysis of which alternatives will address which requirements and functions, the system engineering team can then select a concept to continue exploration with the design and interfaces. This approach works best if the requirements and functions are believed to be correct and few changes are affected. However, this approach may be time-consuming in order to collect and analyze all the alternatives. If more promising alternatives emerge after the analysis phase has been done, then there may be wasted time and return to the analysis. An agile system engineering approach would perform similar actions with analysis of the alternatives, but perhaps look at a smaller segment of the system. This may be performed multiple times in case additional candidates were discovered and considered, as well as how this may integrate with other portions of the system while the work is in progress. It is helpful to lay out the concepts in similar fashion and appearance, quickly turning around the analysis. And if different groups are conducting the study, it may help to share feedback between groups. This approach can respond well when there is a good deal of change with the system concept. And finally, we'll do a summary review of what we've spoken about in this lecture, in this chapter. First, evaluating and selecting the system concepts. Objectives of the evaluation phase are to analyze a range of options that were developed in the previous chapter when a system concept was under development. Decision makers will be cognizant of the system performance as well as the development schedule and cost when making decisions regarding the concept to advance to design. For alternative analysis, the full alternative space would be considered when evaluating the design to satisfy the functional architecture development in another chapter. After the functions for the system concept have been defined and validated, the system engineer should then consider how the design may be developed in order to effectively execute the functions. Evaluating all possible combinations of design may provide a starting point and eventually provide the decision makers with a limited number of feasible system concepts to progress to design. For operations research techniques, the system engineer may perform some analysis on the problem in order to calculate the best performance and cost combination when considering the full alternative space. LP techniques seek to minimize or maximize the objective function. Decision analysis techniques can help to visualize the decision space possibilities when determining the best solution to pursue. For economics and affordability, the system engineer should be cognizant of affordability assessments, which may help decision makers understand the resource allocation process, helping to quantify stakeholders' expectations, and helping to deliver portfolio outcomes that stay within budget estimates. Elements of affordability to be considered at this stage of system development include cost estimating and analysis, investment decision analysis, and resource effectiveness. For events and decisions for consideration, some of the decisions that are made throughout the system engineering lifecycle will affect how the system will maintain its schedule for development and operation in the intended environment. System engineers should understand the decisions that are made during their system development and will affect the remainder of the project. For alternative concept development and concept selection, system engineers will compile all of the work to present to decision makers regarding the different alternatives that have emerged through the analysis, prototyping, and initial conceptual design. System concepts are evaluated in terms of 1, operational performance and compatibility, 2, program cost and schedule, and 3, risks in achieving each of the above. Program risk can be considered to consist of a combination of 2 factors: likelihood that the system will fail to achieve its objectives, and impacts of the failure on the success of the program. Program risk can result from a number of sources: unproven technologies, difficult performance requirements, severe environments, inadequate funding or staffing, and an unduly short schedule. Trade-off analysis is fundamental in all systematic decision-making. For concept validation and concept selection, trade-off analysis should be organized, set up as a distinct process, exhaustive, consider the full range of alternatives, semi-quantitative, use relative weighting of criteria, comprehensive, consider all major characteristics, and documented, describe the results fully. Justification for the development of the selected concept should show the validity of the needs to be met, state reasons for selecting the concept over the alternatives, describe the program risk and means for containment, give evidence of detailed plans such as a WBS, SEMP, and so on, give evidence of previous experience and successes, present lifecycle costing, and cover other relevant issues such as environment and impact. In terms of traditional versus agile system engineering, concept evaluation needs attention by the systems engineer in order for the outcome to be known in a timely manner. Agile approaches may help by presenting the competitive concepts in a similar manner, sharing views between analysis teams, and effectively performing quantitative evaluation of the leading candidates. All right, well, thank you very much.